let's get started. And look at that. The first change is I have a whiteboard. Now, the main content of this video will be evaluating the new version of my power supply where I added a voltage regulator. The design had been done in a previous video. So let's first go take a look at the data we intend to collect and what my predictions are. So first off, we'll look into the voltage after the transformer. Next up will be the unregulated DC voltage. Finally, we'll get into what is new, the regulated DC voltage. Now, just as a reminder, this is what the power supply schematic looks like. The part that most interests us is the stuff towards the right, which is the regulation part. So, as it turns out, I don't expect the results of the AC waveform to be any different than the old version, and those results you can see on the screen right now. Under the no load condition, we should find a fairly decent looking sine wave going from about 15 volts to minus 15 volts. In the full load condition, I would expect us to find that weird looking square wave going from 9 volts to like minus 2.5 volts. Looking at that waveform, the full load one, I am not sure why the negative does not have as large of a magnitude as the positive. That may be something I'll look into deeper later. Also, the reason for the distortion in the full load condition, I have discovered is that the little transformers, like the one I have used, generally operate close to the saturation because they are so small. Transformers could be a whole video by itself one day. So we should probably just move on, and my advice would be to take with a grain of salt what I just said about transformers, because I haven't looked into them as much as I should to be taken as like, oh, this is gospel. So anyways, let's move on. Well, I have to sort of shift myself around here to get into my slides. But now, next up is the unregulated DC voltage, which again we expect to be unchanged from the previous video with version 1, which is basically like 15.7 volts in the unloaded scenario and like 9.3 volts in the loaded scenario. So I'd be remiss to say, though, that we also expect this ripple. You can see that, I don't know if that's orange, like not the blue line in the full load analog discovery 3 output that you can see on the screen now. You can see that we see a little voltage ripple of that unregulated DC voltage, which we expect to see again. Finally, we are going to take a look at what is new, the regulated voltage, which, as you can see there, the equations and calculations here are from page 9 of TI's wonderful datasheet. Link is in the description, and they show us that we should expect a voltage around 2.7 volts to 9.5 volts. I also expect us to find that the ripple on the regulated side will be minimal compared to the non-regulated side. And by the way, I should have mentioned this before, the variable resistor in the bottom right corner goes from 0 to 10K. Now those equations probably make a lot more sense now. But wait, we are not done yet, because before I even got to the evaluation, I found a little problem with the design. I have no minimum current being drawn out of the regulator unless a load is connected. So, unless a load is connected to the LM317, or like my power supply, the LM317 is not going to behave properly. The LM317 requires a load, and looking at page 7, which of those graphs you should see in the left-hand side of your screen, we require a current of around 1.4 milliamps to be drawn out of the LM317 for it to operate properly. That means that with no load, the regulator is going to push the output voltage to 5.9 volts in the minimum condition, and to 19.9 volts for the high voltage condition. However, our input voltage is only around 15 volts in the no load condition, so I'm guessing that we'll see around that 15 volt mark. The LM317 does this to get the minimum current when it is not being drawn out. So I think you can see my calculations at the top right. We have the high value, 14.2 kilo ohms times 1.4 milliamps equals 19.9 volts, which we won't be able to meet because, well, we only have 15 volts in total. And then the 4.2 kilo ohms times 1.4 milliamps is 5.9 volts. So that's where we get to those. For the next version of this power supply, if I do one, I will put the indicator LED after the regulator and design it such that that minimum current is met, so that we do not have this design flaw. Well, with all these predictions out of the way, shall we mosey on over to the bench and start some analysis? First stop is to test the loaded and unloaded voltage and the waveform that we'll get with it after the transformer. So I always check it with the multimeter in case it is higher and it would fry out my AD3 and possibly my computer. So let's just make sure that we are at a manageable voltage. So it's saying 13.1 VAC. We know that we're going to see probably a plus like 15 to minus 15, and then this is just the average. I just wanted to emphasize that this is an important step in the analysis to safeguard my equipment. I use the analog Discovery 3, which I just looked up, has an input range of plus or minus 25%, or 25 volts, not 25%, 25 volts. And it happens to be grounded to the laptop's ground. That means, as far as I understand, if one was to apply, say, power mains, 120 volts AC, that could end up damaging the laptop it is attached to. I have attached the 83 spec as a link in the description, and I do encourage you to look at your own test equipment's specifications, just in case this could be a problem for you as well, and something to watch out for. As you can see, we have this, the channel 1 right up there. Let's turn that scope on. Now let's plug it in. Oh, oops. I want to be looking at 10 times, sorry. Now let's plug it in. There. So, we're at 1 millisecond per division. Let's go to 5. And you see we are getting that same sort of waveform, the one that we expected to get from before. So that's good. Confirms our expectation. Now, let's see what happens when we load it. So we still are not at that weird ass one that we can get it more. We're going like this, because that drops more into the thing there. Let's just set these, and then later I think we will actually look at how much is being strewn across. Actually, we could probably do that already. But yeah, we might bring the multimeter back just to see once we have the waveform we expected to get. We'll just keep loading it a little bit. Little bits by little bits. Let's bring back our multimeter here. Bench is getting quite busy. There we go. So we'll just switch this actually over to the amperage side. Then I'm just going to disconnect this. Then you see we go all the way back up, connect it here, and connect there. See, we're only at about 61 milliamps there still. Still not at the full load. Let's add a couple more. We just want to make sure that we get to our full load potential here. Oh, we already had one connected there. I do have the PPK2 as well, but I think this would be better. We are adding quite a lot there. Add one more. Now this is at 91 milliamps. That, I think, is good enough for us. So let's actually disconnect this. Plug it back in. And we will move the multimeter out of the way again. And you see we got the waveform is quite distorted. It is as expected, but remember, when we were looking at the last picture, I think maybe the picture I took there must have had this shifted a bit, because you see we are going from but just over like would be like maybe 11 volts, 12 volts to the same. So it is bouncing back and forth like it should. Hey, so to recap this part, we found exactly what we expected in the unloaded condition, which is in the bottom left corner. But when it was loaded, we got a different result than we did with the first. Isn't that surprising when you think about it? Because we went from 11 volts to minus 11 volts this time in that weird ass square wave distorted version. And last time we got this last time. So this is like, it's weird because the negative magnitude, and I noted this in the intro, the negative magnitude is different from the positive magnitude. And it is also, the positive magnitude only gets to 9 volts. I don't know if maybe I was oversaturating that transformer when I did this. I guess I'll never really know for sure because I didn't have recorded evidence or anything of it. But it makes me want to go back and look at those previous results and determine if something is off with that one I built, or if my method was off somehow. I would actually lean towards the method, mostly because I haven't been as precise or how as careful with my data as I should be, which I promise will change in the future. Either way, this is what we got with the newest design, and it makes more sense than the previous results. So with all that being said, shall we head back to the bench and look at the unregulated DC voltage? You see, with the unregulated DC, we are getting just above 15 volts, basically. Remember, this is a times 10 value right there. So just above 15 volts. Now, yeah, so it says, let's go look with the multimeter as well. Yeah, so we are actually getting 16 volts according to my multimeter, which is the better one to look at because we do have this scale here. Okay, now we will plug in the ground here, light up all those. Now you see we're getting the ripple. We drop this down to 10 volts, and we did have it up to about 91 milliamps. So we still aren't seeing as much of a drop in DC voltage, or like a DC and AC voltage, when it comes to loading it up as we had expected. So let's zoom in. Here we'll go to 100. Then we'll change the offset to 500. Nope, a little bit more. Full volt. There. Go a little bit smaller. So now here, I'll just pause this scope. I just wanted to demonstrate this ripple more. So the ripple here is going from, what would that be? About 1.025. 1.025 to almost. So ripple 1.025 minus, I would say 0.975 equals, remember, we'll multiply both these by 10. So we get 10.25 minus 9.75 equals 0.5 volts. So we are getting about the same ripple as we had before. Now, let's go to the regulated voltage. Now we will first do the non-loaded version. Let's disconnect that. So, we expected 15 volts. We're actually getting 14 volts. Result. Yeah. So, 14.2 volts, we'll say. For this one, we're really just wanting to focus in on the ripple. And you see, we are having a very minimal ripple. We'll just mark that down. Minimal ripple. We'll compare both the ripples here soon. I'll plug in the other scope probe and we'll compare it. Yeah, so now we will do though this here. Ooh. See, we go all the way down to 5 volts. Now I'll have to change this to probably this. Yeah. So now we have closer to than expected the 5 volts. So we're getting 5 to 14.2 volts instead of the 5.9 to 15 volts. Both minimum ripple. Now let's load it up. And
We got 2.7 basically, 2.655. So we'll put 2.7 volts because we're only gonna put the 2 uh, voltage, and that's a fairly minimum ripple still. Now we will jack it up. We got craziness going on. So here, oh, we are getting a ripple now, though. You see? Go. We are getting a ripple. That is unexpected. Dash 8.7 volts output. Yeah. So you see, they're at about the same range. And yeah, they are showing about the same ripple.
So, as we just found out, the power supply I made has the same ripple as the unregulated part of the circuit. This is not how it is supposed to be. Now, what I have included in the top right corner is the dropout voltage graph of the LM317 from page 7 of the datasheet. Now, looking at that graph, it seems to me that the dropout voltage would be around 1 to 2 volts, but it is hard to tell because the graph is not that precise at the start, and that's where we will be operating, because that's the quiescent current coming out. So we will be operating around between that 0 and 1.5 milliamps, so like 1.25 milliamps of that one. So it should be around that 1 to 2 volts when I look at it. But then if you looking at page 6 of the datasheet, there are two values that are written to be valid for a V in minus V out of between 3 and 60 volts. That makes me think that the dropout voltage is actually close to around 3 volts. So that's what we're going to be going with. I have a new prediction. The regulated voltage will be as expected, as in there won't be any ripple, when a voltage for voltages below 7 volts as the output. This is because a dropout voltage of around 3 volts, maybe a little bit less than 3 volts, will be satisfied. So let's go test that theory.
Okay, so here we are. I'm just showing that, yeah, we got the same ripple. The top one there, that orangey color, is the regulated DC voltage, and the blue one is the unregulated, and you see they have the same ripple. Now, we did show that earlier, and now we just want to test, because I was looking at the data sheet, as I had shown, and we decided, hey, it's probably that we don't have a large enough dropout voltage. So now, let's just go twist this, so we'll lower the voltage. You see, we already, yep, now we got it's already disappeared almost, not quite. A little bit more, oops. Yeah. So at about 8.4 volts, we have enough distance between the input voltage and the output voltage that the ripple goes away on the regulated portion. Yeah. So I would say I still was able to successfully make a about 3 volt to 8 volt power supply. Anyways, let's go back and we will analyze, and I will review what needs to change for a future version.
So I just wanted to end this video going over the 2 design flaws that I found in the design that will be addressed for the next version. First off, I did not supply a minimum current out of the DC regulator. This resulted in us having a voltage range of 5 volts to 14.2 volts when no load was connected, which is much more than the target of 3 to 9 volts. My plan to fix this is to move the indicator LED to a place such that it will provide that minimum load. Right now, the LED is over on the unregulated portion of the circuit, which we don't really need it there, so we might as well move it over to the regulated portion to give that minimum load to the regulator. The second flaw was found while testing, and it resulted in us seeing a voltage ripple equal to the unregulated ripple on the regulated voltage side. Now, we did test that just towards the end of the video to see if it was due to the dropout voltage, which I theorized also towards the end of the video. And it turned out that that was the problem. We just didn't give enough space between the input voltage and the output voltage of that linear regulator. Given that, I'm leaning towards getting a different transformer that outputs a higher voltage so that the unregulated side of the circuit has a little bit more voltage, like maybe a volt or more, and then we would be fine. Yeah, so that's how I'm leaning towards fixing it. We could also design it so that we would have a smaller max voltage, but I'm leaning towards that first one, where we'll just raise the voltage of the unregulated side. But that's all for now. I do truly hope you've enjoyed this video and appreciate the extra planning and layout that has happened. If you have any advice or comments, please comment below. And if you did enjoy this video, please like and subscribe.